This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
Okay, so welcome again. This is lecture number 7, I believe, today. And the topic was interpolation, polynomial interpolation. So what is the basic idea behind polynomial interpolation? The basic idea is I give you n plus 1 points, and the computer should generate the unique polynomial that passes exactly through all these n plus 1 points. And I've been talking about these different approaches to solving that problem, and one had this name associated with it called Aitken, and you asked the question about what are the basis polynomials there. Then the other one had this name Lagrange associated with it, solving the same problem. And then the other approach is based on monomial basis functions. And so I talk about this today again to see the relationship and ultimately make the point that it's all the same result, but a different approach and different representation. And then at the very end, I would also say, well, this is all good, but it's not good enough. Why? Because if you compute an nth degree polynomial, it will oscillate, and we don't like oscillations. So in the end, we have to forget all of that and then go from polynomial to what is called piecewise polynomial interpolation. Why? Because if we just have a bunch of pieces of lower degree, then we will not have oscillations. So that's the outline for today. So let's go again to this first approach. And again, there are multiple approaches to deriving these unique polynomial interpolants. And this one approach has this name Aitken associated with it. And the idea, again, works as follows. And I come to the example right away. So I sketch an example. Maybe 3 points are given to us. And these points have names P0, P1, and P2. And we arrange them in a scheme right away. So there is some kind of scheme, the Aitken scheme, that goes with it. So in the first column, we put the original points, P0, P1, and P2. And since they're the originals, or of generation 0, they have the superscript 0. Okay, and then 2 points, or 3 points, means they have to be corresponding parameter values. And the parameter line is called time. And say we put these values here, and we want to evaluate there. And this would be T0, this would be value T1, and this would be value T2. Again, I have not talked about how we compute the values for the TIs, separate topic. And then Aitken is based on repeated linear interpolation. Okay, so we have 2 segments, we have 2 intervals. What do? We take the first segment, the first interval, and we interpolate for this value there. Okay, so in the first step, we take this interval, and we want to evaluate that line segment for that location. So obviously, we have a ratio alpha to beta to consider. And where is that? Well, this will go into this line segment. We also have to extrapolate here, and we get this point. And this is a ratio alpha to beta. And then we have to use this line segment and linearly interpolate over this interval at that same location. So let's say this is a ratio beta to gamma, and then this configuration would be mapped onto this interval, and the intermediate point would be somewhere in the middle. Okay, so you can say this was the first of 2 steps. I have 2 more points, and I give these points names. So this is now point 0, and this is point 1. But they are of the generation 1, so they have a superscript 1. And the originals, as I said before, are of generation 0, so they have a 0 as superscript. So from these, we obtained 2 new points, which I called P01 and P11. And 2 new points means new polygon, or in this case, a polygon just has 1 line segment. Here is a 1 line segment. And now I interpolate along this line segment using the entire domain of the T line from T0 to T2 and evaluate it at this location. marked by the star. So now I use this configuration here, and I say this is a ratio maybe A to B, and I map that ratio, A to B, onto that one remaining line segment. And so the point would be this point. So now I split this segment in the ratio A to B. And this would be the point P on the curve. So it's P0 generation 2, P sub 0 super 2. And here it is. Here's the final point, P0, 2. Now, if I do this for a varying value, right, this was just one particular t value for which I interpolated. If I let this value t vary between t0 and t2, I will trace out a curve that passes through all these 3 points. And the curve, of course, will look somewhat like this. Right, that's the unique polynomial that passes through there. There is only one, and you get points on this one curve, looking like this. Okay, now what I did here, just by visual inspection, I can also formalize, and I can write down how I actually use certain ratios of t values to linearly interpolate. So, and I put these weights on this scheme. So I multiplied by something, divided by something. I divided by t1 minus t0, right? That's the normalization part. Divide by t1 minus t0. Divide by t1 minus t0. And what goes into the numerator? The first point gets multiplied by the right one, which is t1 minus t, t1 minus t, and here it has to be t minus t naught. Okay, now for the second linear interpolation step, I use a second interval, so I have to divide by the length of it, that is t2 minus t1, divide by t2 minus t1, divide by t2 minus t1, and numerator, left point gets multiplied by the right interval, which is t2 minus t, so this is t2 minus t, and here then it has to be t minus t1. And in the last step, I do a linear interpolation over the entire interval, so I have to normalize by t2 minus t0. So the ratios here, or the weights or multipliers, are t2 minus t0, t2 minus t0. And the denominator, and in the numerator it is t2 minus t and t minus t naught. Okay, so what does this notation mean? It always means that I take this point, multiply it by that, plus this point multiplied by that gives me the next point. That's the way you should read that scheme, right? So always times, 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 and then you add the results. Okay, so this point times that plus this point times that gives you that point in the scheme. And you do this all over, and you see that you could write this as a double loop, right? So you column 0, column 1, column 2, and so forth, and then you do it for all the rows. And you see the pattern, how the index goes, and then you have it. Now, someone asked a question about the basis functions. What are the basis functions here? Is there a polynomial basis function when I derive this interpolating polynomial in this way? Do I have a polynomial basis function here? You asked this question, right? So I asked you to be prepared to help me find the answer, right? What are the basis functions here? The basis functions here. The basis functions here.
So you have the basis for divided differences.
Mm-hmm. It looks like the divided differences, right? But what are the basis functions here? The basis functions are related to these weights, right? Mm-hmm. And they're only linear. And I apply the linear basis functions over and over again, except that I apply them over wider and wider domains. Okay, so in this particular example, it is just a repeated application of linear interpolation, so therefore the basis functions are linear polynomials over the t-line. It's repeated linear interpolation So therefore, the functions, or the basis functions in a sense, that you operate with are always linear polynomials, linear basis functions over the parameter line. Use only, repeatedly, linear basis, in a sense, basis polynomials. Okay, so in this particular example, there were two steps. First step and second step. First step, second step. And so for these two steps, we have basis functions, right? So in this example here, for n equals 2, we have in the first step, certain basis functions, and they are the linear polynomials over the t line, t0, t1, t2, t0, t1, t2. And here is my line that has the height value 1. And so the linear polynomials that I'm dealing with over the first interval are the line that starts at 1 and goes down to 0, and the one, or linear polynomial, that starts at 0 and goes up to 1. And the other polynomial I deal with is 1 here, goes down to 0 at t0, and the other one starts at 0 at t1 and goes up to 1 for t2. Those are the basis functions here. In the first step and the second step, I again use linear basis polynomials, but now the way I use the basis functions, I use them over the entire interval from t0 to t1. Okay, so here's t0, here was t1, and here's t2. And now I do one big linear interpolation over the entire domain. The first polynomial starts at 1, goes down to 0, and the second one starts at 0 and goes up to 1. Okay, and those figures over there correspond to these weights, so these linear polynomials. Right? That's it. And so if I have more points, then I have more levels of these nested functions, in a sense. Does this make sense? Okay, you can multiply all of this out. Okay, if you multiply everything out, then you have to get one unique basis, right? You get one unique curve. It's one unique polynomial. When you multiply everything out, you get the monomial basis. Okay, so far so good. Then there is the other approach to doing this, or deriving it, and that was approach number 2, carrying a different name. By the way, there are many, many more approaches to this, not just the 3 that I talk about. The next one I chose to talk about had the name of Lagrange. 2 was Lagrange polynomials. And so the basic idea, let me just sketch the example. Example for n equal 2 again. N equal 2, we have a point, and a point, P0, P1, P2, and we have the t-line, and we have the line that is 1, and we have 3 parameter values, t0, t1, and t2. I have to make them a little bit further down. T0, T1, and T2. And I want to have the polynomial that passes through these points. This is the curve P of t. I want this polynomial have a particular representation. I want it to have a representation such that the given points are the coefficients in that representation. So that P of t is a sum, I from 0 to n, and I use these basis polynomials, Lin of t, those are the Lagrange polynomials of degree n, and the weights in front of them, or the coefficients, should be the given points, P sub I. That's what I want. Okay? And if I want this representation, then these polynomials have to be of a certain shape, or of a certain kind. This is the desire. The desire is that the points, given points, are the coefficients in this representation. Given points, given P and Ts, are coefficients. Coefficients. Okay. If I want this, then these polynomials, Li, n, at any of the knots have to have a certain characteristic. And they have to have the value 1 if j is I, and they have to be 0 otherwise. Okay. So in this example, I have a polynomial L0, a polynomial L1, and a polynomial L2. Okay, and each of these Li's should be 1 at I, Ti, and 0 at the others. So the first polynomial, L0, should have a value 1 here, and it should have values 0 here and 0 there. So there is a unique quadratic polynomial that goes through these three locations, and it will look like this. Right? You believe me that that's the one parabola that goes through these three. The next polynomial, L1, would be 1 here and 0 at the other locations. Right? So it will have a general shape that looks like this. You believe me that that's the case? And the last polynomial should have a value 1 here and 0 here and 0 here. So the last polynomial will have a shape like this. It has to go this way. Okay, so these are the general shapes of those polynomials. So again, this guy would be L0, 2 of t. This guy would be L1, 2 of t. And this polynomial here would be L2, 2 of t. Okay, this is just a sketch of the general shape of these functions. Okay, now I also need a definition. I need to evaluate them, not just a sketch. And then there's this formal definition from then the polynomial coefficients for these Lagrange polynomials follow from this exact condition. And then you actually get the explicit definition of these guys, and it's Li degree n of t is, and then it was this huge ratio where you have two products j from 0 to n, and j different from I of t minus tj, and then you divide by product j from 0 to n and j different from I, and it is t sub I minus t sub j. Okay, this is what you need for your practical implementation, a function where a t goes in and the value of L comes out. So this is very nice because you get this very beautiful representation, this one. Okay, the points themselves are combined in this way, are multiplied by these Lagrange polynomials. Okay, so this is very cool. And then there comes another approach to derive this unique curve, and that just spells out the interpolation conditions explicitly, and you end up with a linear system of equations. Last but not least is number 3. And that is based on the monomial basis, using use of standard monomial basis. So here these guys are the basis functions, right? These are the basis functions. Basis, FCTS, basis functions. And now we use the monomials. So the basis bases are just these powers of t, right? So t to the zeros is just 1. If this is a 1 line, then t and t squared and t cubed and so forth. So the different powers of t are the basis functions. Right? So the basis is a set of functions 1, t, t squared, blah, 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 t to the nth power. Okay? Those are the monomials. And so here would be t, and that's the sketch, right? The higher the power, then all these polynomials will be pulled into that corner. What does it mean? So you want, again, for a given set of points, let's use our example again, n equals 2, just to sketch the problem over and over again. It's always the same problem. It's P0, P1, and P2. And you have your parameter line, t, on which you have the designated values, t0, t1, t2, where you want to interpolate. And you want to get this curve, an explicit representation of that. And the explicit representation that you want this curve to be written in is as follows. You want the representation p of t is sum I from 0 to n. And now you want the monomials, t to the i's power, to be the basis functions, okay? And then you do not know what the coefficients are in front of it. And I just call them a sub I. Now these are multiple components, right? Point P has x and y, and the coefficient has to have an x and y component because it's a curve. So the unknowns are the coefficients ai. How do we get them? Well, we get them from the constraints that this polynomial should interpolate n plus 1 points. I have n plus 1 coefficients, I have n plus 1 interpolation constraints, I get a linear system of equations. I just have to write them down, what they are. So, linear system of equations, Okay. I evaluate the polynomial for the first t value, and I want to interpolate p0. I write this down. And then for the last parameter value t sub n, I plug t sub n into the expansion there, and I want to interpolate the last point, p sub n, and I write this down. Okay, so that's all that I'm doing. So I say a0 plus a1 t0 plus a2 t0 squared plus blah 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 plus a sub n t0 to the nth power equals the first point, p0. It's the first condition. I plug t0 into the equation, and I want to interpolate p0. And so I have a bunch of these, and the last one that I get, the last one is a0 plus a1, the last parameter value, tn plus a2, tn squared plus blah, 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 plus a sub n, tn to the nth power should interpolate point n. Okay. And I have a bunch of equations in between. And now I can also write this in matrix form. So you see that you really are dealing with a linear system of equations. So the other two schemes are representations or derivations of these polynomial interpolants. Aitken or Lagrange didn't require you to deal with the linear system, but this monomial approach does. Okay, so I say this one is the important system, and now I write it in matrix form, so I call this star. So star in matrix form. Write star in matrix form. Matrix form. So there's this huge matrix, and what is in it? There's 1, there's T0, there's T0 squared, and then bam, 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 and the last one is T0 to the nth power. Okay, and the last line, what does it multiply? It multiplies the coefficient vector A0, A1, times AN. And I want to interpolate the given points, P0, P1, and the last point is Pn. Okay, and I said the last entry here is 1, T sub n squared, and the last entry in the whole matrix is T sub n to the nth power. Okay, so I have a nice full-blown n plus 1 by n plus 1 matrix. This is an n plus 1 by n plus 1 matrix. And it also has a name. It is called the Vandermonde matrix. Does this all make sense? What is going on here? And what do you have to do in this case? Right? The goal is to write the unique polynomial that passes through the n plus 1 points in this form. Right? You want a representation value of coefficients times the powers of t. What do you know and what don't you know? You do know the points, p0, p1 up to pn, that you want to interpolate, and you don't know the coefficients. Okay, so now what do? You write the constraints down explicitly, namely, you plug the different t sub I values in there, and you force this representation to take on the points that should be taken on by the polynomial, p0 up to pn. Okay? And then you have to deal with this full-blown linear system. So linear system of equations. Linear system of equations. How expensive is it to compute the coefficients now? A0 up to AN. Is this cheap to do, or is it expensive to do that? Yes, why is it expensive?
The Gaussian elimination.
The Gaussian elimination will be very time-consuming here, right? This matrix is not a special matrix in any way. It is full-blown. It is not bended. It doesn't have any zeros in there. It has values different from 0 all over the place. So, and what is the usual time when you have to invert a matrix with standard Gaussian elimination and you cannot take advantage of any special characteristics? Then n cubed, okay? So that's big, okay? So this requires typically, so I just put this here in the middle, typically, if you don't play any tricks, typically O(n) cubed time, right, for inverting that matrix. So you have to do some tricks, and that is in your linear algebra. So
You can always, is there a case where you can't invert it? Or the way you set it up, is it always invertible?
the way I set it up, it's always invertible. Okay, when will bad things happen? Bad things will happen when I do nasty stuff, like like putting some of the t values on top of each other, but which I don't allow. Okay, so t1 should be bigger than t0, t2 should be larger than t1, and things like that. If that condition holds, then everything is fine. Okay. If you don't do strange games with the values of the ti's, then everything is fine. But dealing with this matrix is numerically unstable, and it takes a lot of time, and it's not good at all. Okay. So therefore, if you look into this more deeply, you have to look into things like speeding it up and using schemes to orthogonalize the problem. But I just put the words on here, so you want to look into things like an LU decomposition, or orthogonalization, or orthogonalization. Those two things will make things better. But just general recommendation, we will not be dealing with this approach in general. You should avoid that. check whether I forgot anything. No, I did not. Then we can go forward. Okay, so all I talked about was polynomial interpolation, right? This is all the same thing that I talked about. One problem. I give you a bunch of points and give me the one unique curve that passes through the points. And I use different ways to compute points on that curve, right? Is this all we need when we want to interpolate? Is this one unique answer the best answer you want? Are these curves that you get from these good curves? Do these curves look good? Are they good? Do they solve the problem? Well, they solve the problem. Right? By construction, they solve the problem. But are they good curves?
Perfectly periodic, use track basis. If you want local, use line basis, things like that.
Very good point. Local. He said he used the word local. Local and global. Here the answer, what if I change one point? If I change one point, what happens here? I mean, this representation shows you that. If I change just the location of one point, does it have a local effect or it has an effect on everything, right? If I change one entry on the right-hand side, I have to resolve the whole thing, right? I have to recompute, and all the coefficients will be different, and the entire curve will look differently everywhere. That's bad. Okay, so this unique global polynomial depends on each single control point or point to be interpolated everywhere, which is a global scheme. That's not good, right? So, for example, if you have a nice interpolant from a hand and you just want to change locally and pull one thing out, one point out, then the whole hand interpolation changes. You don't want that. Right? That's bad. So we want to have a scheme that is more local. The other thing is here. You deal with huge matrices, order of n cubed, and you have to worry about orthogonalization and Gram-Schmidt procedures and decomposition of matrices. Do you want to do that? No. Do you want to deal with these huge Lagrange polynomials, these endless sums, product of a bunch of terms, like n, I guess? No, it's expensive, right? Also numerically not nice. You divide it by some stuff there in the Lagrange version. You want to have local control over a curve, and you want to have low degree, right? If you have low degree, n is low, the computations are fast. That's what you want. And the other thing that you want is local control. I change one point, and changing that one point only should affect the shape in a local neighborhood, but not far away. And then there is another issue that has to do with oscillations and wild behavior. Did you mention that too? Or you mentioned that, or? There are oscillations, okay? So this goes on the idea board. So what is bad? Bad. Well, or disadvantages, right? Bad about the unique nth degree polynomial interpolant. Polynomial interpolant. Okay, number one was I change one value and it has an effect everywhere. Let me see whether I can sketch an example for that. It's a global scheme, and I'm thinking already about an example where I can show that. It's a global scheme. And that means no local control. No local control. Okay, I think I can think of an example here and here. T is the same T line, and I give you 1, 2, 3, 4 values. 1, 2, 3, 4 locations on the T line, and function values there. And the first curve should be 0 at all these locations. It should be 1 here and 0 here. I mean, I explained it for the functional setting, but that's besides the point. You will see what I'm getting at. So if I have a polynomial curve that should interpolate 0, 0, 1, and 0, then the curve has to look like this. Right? Okay, now I only change one value. I change this and I flip it over. Okay, I make, instead of +1, I use -1. Okay? So here I use this value and put these guys here. And you will see that everything changes, right? And now it, right? This, everything flips, changes everywhere. And the other thing is the oscillations, right? Oscillations. And typical example, I give you a bunch of locations where the values should be 0, even on a line that already shows it. And here it is 1, and here it should go down to 0 again, and here it's 0, and here it's 0. The one polynomial curve that will pass through this will wildly oscillate all over the place. It has to. It will look like this. Okay, and these oscillations go on forever. Right? If you have 1,000 more t values to the left, even at the very end, there will be the oscillations. They have to, because you have to have this swinging behavior, right? Undershooting, overshooting, undershooting, overshooting. It goes on, right? And forever. You don't like that. So if you design a car body with that, you would have bumps all over the place. Not good. And the other thing is computational cost, right? It's too expensive in general. Computational cost. Computational cost. Okay, so these are all the bad things about the polynomial approach, the global polynomial approach. And so if there's a global approach, then there also must be something that is called local, piecewise polynomial approach. And those curves are typically called spline curves, or splines. So the next topic is piecewise polynomial. Piecewise polynomial interpolation. And then the buzzword is splines, or spline curves. What is the simplest piecewise polynomial curve that you can construct? Piecewise polynomial, PW, piecewise, okay? Piecewise polynomial. Okay, if I give you a bunch of points to be interpolated, what is the simplest piecewise polynomial? What is the simplest polynomial? All that we need to know in this class is lines, right? Or linear interpolation. So the polygon, the polyline is the simplest one, right? You construct a piecewise polynomial curve. It has 1, 2, 3 pieces, 1, 2, 3 pieces, and all pieces are line segments, linear polynomial. So this is a piecewise linear spline curve, right? It's a spline, a linear spline. A linear spline curve. Okay. Now I can use line segments. What else could I use between two consecutive points? I have point, point, point. Is a polygon always at what you want? Or what other shapes do you want? What else could you specify at the points besides the location? Maybe derivatives or slopes or tangents? You could say that the curve should start out in this direction, right? It should have this slope and at that point, and it should have that slope there, or that velocity. So I specify points and derivative vector. So then the answer for this would be one curved segment that looks like this here, right? One cubic segment, 2 points, 2 vectors at the ends, 4 degrees of freedom are taken, right? So it has to be a cubic curve. And then again, 2 points, 2 vectors give you another cubic curve. It would have to look something like that. Okay. And here, of course, they have the same slope, right? By construction, because they have to share that vector. Get that? Does this help us also with this nasty oscillation business? Yes, it does. Right? So when we think about the nasty oscillations that we had to deal with before, so now, if I want to avoid oscillations, I just say, okay, I specify a bunch of points, but I also specify the derivatives there, and I just make sure that these derivatives do not imply wild behavior, wild oscillating behavior. Okay, so I have the same configuration there, which in general, if you use a polynomial interpolant, would give you this wildly oscillating thing that oscillates forever. But now I say, okay, I specify the points, but I also specify the tangent vectors, or the slopes in this case, at these points. Okay, and now you want to have cubic segments, right? Each cubic segment would be point, vector, point, vector, right? Then you get one curve. And you do this here all over the place. So point, point, and horizontal vectors means the connector is line. It's a cubic curve, but it degenerates into a line, right? The way it looks. 2 points and 2 horizontal slopes, so therefore it has to be that curve segment. And here, 2 points, both with horizontal slopes, so it has to look like this. Right? But it doesn't oscillate. Stays flat. Same here. 0, 0, flat, flat. The interpolant has to be flat. And then 1, 0, horizontal slope, the curve has to look like that. It's nice. Local control, much faster computation, no oscillations, and cool. So now we have to see how this is represented. And a particular scheme is based on Hermite polynomials. Important scheme. Is based on Hermite polynomials. So, in general, what is given? Given are 2 points plus 2 derivative vectors at those points, 2 derivative vectors at those points, and wanted is the unique cubic polynomial that interpolates these 4 constraints. The unique cubic polynomial curve interpolating these 4 given constraints. The 4 given constraints. Okay, so an illustration. What is the configuration? The configuration is this. I have a point, I have a vector, and I have another point, and an end vector, and I call them P0, and I call them P0 bar for derivative, and this is P1, and this is P1 bar. 4 bits of information, so the curve that is implied by that would look somewhat like this. Right? So this is the curve I want. So this is the curve P of t. And I will only explain it for curves t where t varies between 0 and 1 for the time being. 0 and 1. And the representation of the curve should take on the following form. Representation. And this is the Hermite representation. Hermite. I want to write P of t as a curve where the points and the derivatives are the coefficients. The point P0 multiplies Hermite polynomial h0 of t plus point 1 multiplies Hermite polynomial h1 of t plus the derivatives, derivative vectors P0 bar multiply h0 bar at t plus the derivative at the last point P1 bar multiplies h1 bar of t. That's the representation I want. And what is it that is unknown to us at this point still? Unknown to us are the polynomials h0, h1, h0 bar, and h1 bar. Capital H for Hermite, right? Hermite polynomials. How are they defined? So we have to look into that. Need to know definition of the Hermite polynomials. Hermite polynomials. How are they defined? Has anyone looked it up already? You've looked them up, right? You know them? These polynomials are responsible for different of these constraints, right? You have to always get to the understanding by intuition, right? Try to get to the meaning of it. Okay, we had this before. In the Lagrange representation, we wanted a representation where the points themselves multiplied Lagrange polynomials. This is very similar, right? Here we want the representation, the curve, the one cubic curve, is obtained by the given constraints showing up in this representation as coefficients, right? The points and the derivatives at the points. And they are multiplied by these H polynomials. Okay. Well, in a sense, it means that this polynomial H0 is responsible for interpolating the first point and nothing else. This polynomial should interpolate the first point and nothing else. There are 4 constraints, and this polynomial is responsible for dealing with 1. That means this polynomial should have the value 1 at 0, should have 0 slopes at both ends, and should have the value 0 at 1. This polynomial h1 is responsible for interpolating p1. What does it mean? It should take care of one constraint, namely interpolating for 1. Okay, so therefore the value of h1 at 1 should be 1, the value of h1 at 0 should be 0, and its derivatives at both ends should be 0, because it only should take care of interpolating the second point. Okay. And I sketch these polynomials, and then I just give you the actual expansions. Sketch of these polynomials. So we have 4 polynomials, and as I say, they live in these boxes from 0 to 1, 0 to 1, 0 to 1, and another box. Okay. This will be polynomial h0 that I will sketch. Here I will sketch the polynomial h1. This is our t-axis, and I only draw it between 0 and 1. So this is 0, this is 0, this is 1, this is t, and so forth. Here I will sketch h0 bar, and here I will sketch h1 bar. Again, the important part was that the first polynomial h0 is responsible for interpolating here at the beginning. Therefore, it should have a function value 1 there. It should be 0 here. And it should have 0 slope at both ends. It should have a 0 slope here and a 0 slope there. Because it's only responsible for interpolating the function value there. The second polynomial, h1, is responsible for interpolating at 1. So it should have the function value 1 here. It should not interpolate anything here, so it should be 0 here. And it should have 0 slope here. And it should have 0 slope here. Okay. Now, h0 bar is responsible for what? h0 bar is responsible for interpolating the slope at the beginning. Nothing else. So it should have values, function values 0 at both ends. And it should have slope 1 at the left, because the slope 1 multiplies the given slope. So this should have the slope 1 at the beginning and the slope 0 at the end, at the other end. Here, h1 bar is responsible for interpolating the slope at this end, so it should have a slope of 1 here, a value of 0 there, a value of 0 here, and the slope of 0 here. Okay. That's the way it is. Right? The first polynomial is responsible for interpolating at the left, so therefore it is 1 there, and the rest is 0. The last polynomial is responsible for interpolating the slope at the right, so therefore its slope is 1, and the rest is 0. That's the way the principle works. Now, you obtain, when you write these conditions down, the constraints for the coefficients for all these 4 polynomials, and I can write them down for you. But first, how do they look like? So this polynomial has to look like this, right? That is the shape of the first cubic polynomial. The second cubic polynomial starts out at 0 and then goes up to 1. This polynomial starts at 0, goes up, and then goes down to 0. And this polynomial has this shape. So it goes down, and then horizontal. So those are the polynomials, and now I write them down. And of course, I have not memorized them. That's just too much. And I tell you what they are. So h0 is a polynomial 1 minus 3t squared plus 2t cubed plus 2t cubed, that polynomial. h1 is 3t squared minus 2t cubed minus 2t cubed. Now h0 bar is t minus 2t squared plus t cubed plus t cubed. Okay, again, h0 bar is t minus 2t squared plus t cubed. And the last one, h1, here's h1, is h1 bar is minus t squared plus t cubed. So those are the explicit definitions of those polynomials that you need. Is anything not quite clear about this derivation or this thinking? Does it make sense? Make sense? These are the basis functions, right? You like basis functions. These are the 4 basis functions that are required to write a cubic polynomial, any cubic polynomial, in terms of its 2 endpoints and its 2 endpoint derivatives. Right? Now we will play a little bit, and we will convert from a Hermite representation to a Bernstein representation. Why is that? Because we like Bernstein polynomials so much better than Hermite polynomials, right? The traditional derivation or representation of these cubic pieces, these cubic segments, goes back to Hermite, right? That's why these Hermite polynomials are there in the textbook, and that's why they are mentioned. But in the standard CAD-CAM system and so forth, everything is based on Bezier curves and Bernstein polynomials and so forth. So we should worry about how to take this ugly representation. These polynomials are very hard. I couldn't memorize them, right? Why would I? Right? But how do we take this representation and convert it to what we can much more easily and geometrically remember? Huh? How do we go from these h's, from the h polynomials to the b, Bernstein polynomials? Okay, so this is now a change of basis. And so we have to see how the given points in the 2 vectors are related to the 4 control points of a cubic curve, right? So the idea now is, if I have a point, a vector, and a vector, right? This is the input for the Hermite scheme. The Hermite scheme takes this information and computes points on this curve directly. This is not what we like. In our Bezier world, Bezier curves, we say the first point is the first Bezier point, the last point is the last Bezier point, and then we need some other Bezier point somewhere here, and then we have a Bernstein Bezier control polygon that is that curve. How do we get that polygon, right, from the vectors and the points? So that's the transformation. How do we get the 4 control points for a cubic from 2 given points and 2 end vectors, right? Now let's do a change of basis. Change of basis. We go from Hermite polynomials to Bernstein polynomials. And the trick is this. This is the trick. You need to know how the Hermite polynomials are related to the Bernstein polynomials. So Hermite polynomial 0, Hermite polynomial 1, Hermite polynomial 0 bar, and Hermite polynomial 1 bar. I can write them in terms of Bernstein polynomials by looking at these figures. Okay. And I draw something here which will help me to write down this change of basis. Make these polygons, and they help me build a bridge. And so they help me to remember that H0 is nothing but B03 of t plus B13 of t. And that H1 is B2, 3 of t plus B3, 3 of t. And that H0 bar is 1/3 of B1, 3 of t. And H1 bar is minus 1/3 of B2, 3 of t. Equipped with this knowledge, I can now do the basis transformation. So originally I said my polynomial, my cubic curve P of t is P0 times H0 plus P1 times H1 plus P0 bar times H0 bar plus P1 bar times H1 bar. And now I plug these substitutions in there for the Hermite polynomials. I replace all the Hermite polynomials by the corresponding sums of Bernstein polynomials. And I get this is P0 times H0 is B0, 3 plus B1, 3, and P1 plus P1 times what is H1. H1 is B2 plus B3, B23 plus B33, and then plus P0 bar times H0 bar, that is 1/3, times B1, 3, and the last one was plus P1 bar times minus 1/3, minus 1/3 times B2, 3. Okay. Now I want to get from this the control points, the Bernstein-Bezier control points. So now I collect terms. What are the things in front of B0, in front of B1, in front of B2, and in front of B3? So this is, I collect terms in front of B0, 3, it's only P0. So it is just P0 times B0, 3. Okay. Now I want to collect the terms in front of the B1, 3. B1, 3 is here, and then it occurs there. So that means it is plus P0, P0, plus 1/3 of P0 bar times B1, 3. Now I want the control point in front of the polynomial B2, 3. So what are the coefficients in front of B2, 3? This one, that is P1, and then here's B2, 3, that's minus 1/3 times P1 bar. So it is P1 minus 1/3 of P1 bar. And then what is the coefficient in front of B3? That's only P1. So it is plus P1 times B3, 3. Okay. And now I have changed it into a representation where I have Bernstein, 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 Bernstein polynomial, and these are the control points in front of it. Okay, so this means that this guy, that my control point B0 is P0, that my control point B1 is P0 plus 1/3 P0 bar, that my control point B2 is P1 minus 1/3 of P1 bar, and that my last control point, B3, is P1. Okay, now this was a formal derivation. Again, everything that has such a nice formal derivation also has a nice picture for it, and all we need to remember here is the picture, what this means. And of course, it's very simple. It is very simple indeed. So, geometrical interpretation, geometrical meaning, okay. So, we are given 2 points, we are given 2 endpoint vectors, and we want to get the 4 Bezier control points from that. Given are 2 points, 2 PNTS plus 2 vectors at those points, and wanted are the 4 Bezier points, Bezier points for the unique cubic polynomial, for the unique cubic. Okay, so I give you a point, I give you the vector, so this is my point P0, this is my vector P0 bar, I give you the end point P1, and I give you an end vector, maybe like this, why not? And I call that P1 bar, this is P1. And where are the Bezier points? Well, these are the Bezier points. Here they are. The first point, P0, is the first Bezier point. The second Bezier point is the first point plus 1/3 along this vector. And the Bezier point B2 is this point minus 1/3 of this vector, so backwards. And then the last Bezier point B3 is P1. Okay, so I just do this. This point is also Bezier point B0. And the last point, P1, is Bezier point B3. Okay, in circles. And now Bezier point B1 is 1/3 along this line segment, or along this vector. So it is P0 plus 1/3 of this vector, so it lies here. This is 1/3, say. Okay, so that would be B1. And then here, we have to flip this vector over and take 1/3 of it. So it is minus 1/3 of that vector, and so maybe that is there. Okay, so here would be B2. Okay, now we have B0, B1, B2, B3, and as always, we connect them by the Bezier polygon, right? Connect, and connect. That's our Bezier polygon. And now you know that the curve that you get will look like that, and that is P of t. And we did this all for a curve just over 0 and 1. Okay. Now, why is this cool? What does this allow me to do? Now that I know how to represent a single cubic in Bernstein form when I specify points and vectors, what can I do now? What can I do? I can do this. I have a very first simple computer-aided design system where I can specify a bunch of points, specify certain tangent at those points, and get a very nice curve that is very nicely behaved in between. Huh? Very simple. And I don't have to do any kind of linear system solving. The geometrical construction for the derivation of the Bezier control points is over there in that simple picture. That's all you need, right? So what can I do now? Well, I can say I give you a point, I give you a vector there, I give you another point, I give you a vector there, and I want to have another point here. I want to specify a vector there, and maybe another point here, and I specify a vector there. Okay, this is the input in which the user thinks, and now the system has to come back with an interpolant to that doesn't wildly oscillate. Well, so what will we do? We will construct a single cubic curve there, one cubic curve there, and one cubic curve there. But since our computer-aided design system is based entirely on Bernstein representation, Bernstein polynomials, Bezier curves, it should now get translated into the Bezier point, into the Bezier control points, right? How to do that? Well, here's a point, then 1/3 up that vector is the other one. Here's one, then minus 1/3 backwards is the other one, right? Then here's a control point, here's a control point. 1/3 in this direction, here's a control point. Minus 1/3 backwards, here's a control point, right? Here, 1/3 along this vector. This is a control point, and now we go minus 1/3 backwards on this one, right? Those are the control points now. So we have the first cubic segment, which has this polygon. The second one has this polygon. And the next one has that polygon. So now I have a first cubic curve here. Right? A next cubic curve here. And the last cubic curve here. It's very nicely behaved. Huh? From here to here, from there to here, and then the last segment there. It cannot behave wildly. It's all very much controlled by the points, the directions of these vectors, and the length. If I want to pull the curve further out, well, then I would just extend the vector. Right? If I pull the vector further out, then, well, the curve will follow. So now you can have a very simple design system where you can do things with this. So for example, if you wanted to have 4 points, like this, and you wanted the resulting curve to be smooth, not sharp corners, but round corners, but very tight to the polygon, then you can have very short vectors there, right? So you specify very short vectors at these endpoints, very short vectors. And then, because this 1/3 business comes into play, the resulting cubic curve here will look very flat. It's nearly a line, but just nearly. It's still curved, right? And so then you here have another one. You have another one. Right? And then when you pull these guys out, then of course you can get all the different shapes in between. Right? So it's quite powerful. So the points themselves and the vectors, direction and length, are the control parameters that allow you to control locally the curve. And whenever you move this point around, up or down, it has no effect on this curve, right? Moving this point up or down only changes that and that. That's it. Okay. The other thing is when you take this vector and make it longer or shorter, it only has an effect on this curve and that curve, but not on that. But everything still comes together smoothly, right? Because by construction, they always share the same tangent at these breakpoints. So it's pretty neat. All right. Let's see how I should transition over to the next lecture. So the next lecture will be again about this particular concept. If I want to represent a very complicated shape with many simple segments, how do I make sure that the different segments come together continuously, smoothly, with the same slope and same normal, or maybe even the same curvature? Okay, so this goes into the topic of continuity, how to make sure that when all these segments, where these segments meet, they meet smoothly. Because you want to look at your Corvette or your Porsche or whatever car you drive, right? It should look smooth, right? When you have reflection patterns on the paint. Right? If the car body doesn't have smooth-looking reflection patterns in it, then obviously it wasn't well designed. So. Okay, I'll see you on Thursday night.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.